whatever I was discussing with you in timer, in interrupt, in analog to digital conversion, all of them focus on writing inputs into your devices. Remember, I was asking you to go ahead, get your keypad to become an input as an analog signal, right? It was analog, but inside the microcontroller, and of course, inside the code, I was teaching you how to activate your converter, how to just control it and convert it. And out of that analog signal, which is going to be inside, converted to digital, at the end, see some digital output. So now, today I'm going to discuss it with more detail. As I said, anything so far, it was about writing an input to the system. And today I'm looking at the output. That's why I need you to learn about pulse width modulation. Pulse width modulation is going to focus on your output rather than input. Simply means when you have a pulse and you want to measure the frequency, then you need to use timer, right? That's why pulse width modulation is going to be an output, because you need to look at the time, look at the change of that input frequency based on the time, and accordingly generate your output through your microcontroller. Therefore, we are going to look at the application of like pulse width modulation. And of course, tomorrow during the lab time, I'm going to teach you how to look at the functionality of your DC motor, and through the pulse width modulation, or PWM, go ahead and look at the speed, or I would say control the speed of the DC motor, be able to control the direction of the rotation for the DC motor, right? Again, DC motor is having an analog signal or digital signal as an input. Which one it is? Who can tell? Analog or which one? DC motor. You are going to just look at your DC motor. What do you have through your DC motor? We are going to control the speed. We are going to control the direction of rotation. How we are going to do that? Through analog, right? But we are going to do it through another different method, and that's called pulse width modulation. Therefore, in this lecture, I'm going to look at the pulse width modulation in order to control the power, in order to just look at the operation of DC motor tomorrow during the lab time, and today during the lecture, I'm going to go over the detail, the steps that you need to take in order to do so. And of course, how we are going to program it in HCS12, since we have like in their header file with some certain keywords that we need to use. And of course, I'm going to show you some C programs. And then later during the lab time, the application of those C programs through the PWM pulse, how we can generate pulse using the method PWM inside your C program. So in terms of the big picture for the semester, we are today looking at the pulse width modulation. Still, we have a little bit more about the interfacing, and of course, the CAN communication, which we are going to discuss them after you are back from the study break. So up to the end of the first half of the semester, still I'm going to continue with the PWM. Means even next week I'm going to continue with PWM, and then you are going to go for the break, and then we are going to finish this part, which is the embedded system, with 2 more topics. Just quick review. In the remaining session, in the second half of the semester, I'm going to focus on automotive electronic. In there, I'm not going to teach you any programming anymore. And some of the sessions also during the lab, that's the time that you have to just focus on your final project. So I'm going to finish teaching the C programming for the microcontroller by the end of CAN communication method, right? And then right after that, I'll look at other aspect of automotive design and, let's say, automotive electronic design in more detail, such as like wiring. At some point, a little bit about energy management, which is more focused on the battery design, and of course, a little bit of cranking system. So let's focus on PWM. The main reason for pulse width modulation is about the delivery method of partial power. Remember, if we are having an analog input, therefore, it's not going to be really easy in order to generate output through that constant analog input and convert it. That was the reason that before we were using analog to digital converter through the microcontroller in order to generate some digital output for us. But in here, looking at the picture in here, we have a DC motor. This is going to be your DC motor. So, and I want to control the speed of the motor. Pay attention. This is really helping you to understand the lab tomorrow if you get that information from now. So, years back, before having the PWM method, in order to control the speed of something like a DC motor, or even control the direction of rotation for a DC motor, very traditional method was adding like a potentiometer. And I'm expecting everybody to be aware right now, potentiometer is just a variable resistor, which you can just set it to different amount of resistance in order to control the voltage, or I would say in order to decrease the voltage. So that was the traditional method for them, to use a potentiometer right in between the power source. This is in here, like for example, this battery, this is the power source, or this is the motor. And then through that, they were trying to just maybe adjust the voltage and control the speed of the motor. Of course, I cannot change the direction of rotation through potentiometer. Can I? No, I just can impact the voltage. But still, for DC motor, if you want to manually change the direction of rotation, this is not going to be something complicated. Every single one of you know DC motor is considered a load with no polarity. It doesn't have polarity initially until you put it inside an electronic circuit with a positive and negative. By default, DC motor doesn't have polarity, okay? So therefore, since it doesn't have polarity, if you connect it to positive and negative one time, suppose that this is going to rotate clockwise. Next time, still the power source is the same power source. If you change the connection from positive to negative, opposite direction as the first time, it's gonna change the direction of rotation if you're supposed to do it manually. And instead of turning or spinning clockwise, it's gonna spin counterclockwise. These are the traditional method, not automated method, not a more updated method. So it's not, I would say, a very powerful method. It's not accurate method. At some point, even not safe method. Therefore, gradually the pulse width modulation technique, which is a way to control analog devices with a digital output. So still input is analog, and instead of A to D, we are using PWM. They just invented this method, and they were able to have the partial power delivery, right? In there, we had like in A to D, we had like interrupt, we had timer in order to stop it and run it, stop it and run, send an interrupt for a new signal or something like that. But in here, we are going to have partial power delivery. So I would say PWM is a method of using pulse width, which is going to be, for example, this is a pulse width. This is a pulse width. This is what we call it. The pulse width means how long it will take for a pulse to be on or to be off. That's what we call it, the pulse width. So this is a method using a pulse width to encode or modulate a signal. That's why we call it pulse width modulation. So we need to look at the width, pulse width modulation. We are modulating the widths. So the width of each pulse is a function of the amplitude of the input signal. Whatever the input signal is, then the width will be modulated accordingly. So if a device is powered by PWM, simply means is going to behave by the average of all these pulses. So I'm not going to get the exact input. It's going to be the average. Why I say average? Because each time when we are modulating the input signal, each time we are assigning it to become on and off, on and off, and on and off. Kids, let's just give you one practical example. Suppose you are sitting inside your vehicle and you are pressing that gas pedal in your automotive. You know that is that one, that gas pedal or the brake, but now focus on the gas, is working using some motor, right? So are you feeling the gas pedal going on and off, on and off, on and off? If so, it's going to be a dangerous situation, isn't that? So when you press it, in fact, technically, it does go on and off. It does go travel through such a signal, but it is happening super fast in a way that, suppose that you are in the stop in the red light, you are just stop, you are not pressing the gas, and then all of a sudden you press it. Of course, even if you have your feet still touching the pedal, this signal is going on and off. But it is happening super fast because pulse width modulation is working based on timer. And the way that we set the timer means we are setting for how long we want it to be on, for how long we want it to be off. And in fact, we are going to filter out the signal through this on and off to convert it to a more constant voltage, right? It is happening, that on and off is happening for your gas pedal, but it is happening super fast, you won't notice it. Therefore, if in any other devices, the pulse width modulation is not happening in a very accurate way, and the time that the off is taken means the zero, I'm going to show this part like with green. If this one is taking long time, simply means if this is your vehicle, you press the gas, but anyway, it has to be converted to PWM. If the off time or the zero time takes a long time, means in the middle of the junction, you may stop. And then again start, and again stop, and again start. Simply creates a very complicated, dangerous situation for yourself and any other driver. So now, as an automotive engineers, you know that that one has the PWM, and it is working with PWM because we are going to control the speed of the vehicle through pulse width modulation, but it is happening super fast. And when I say happening super fast, means this off times or the zeros are small, right? Not for a very long time. That's why we don't see the car to stop and again start. Make sense? Now, looking at this voltage right in here, what is that? This is an example of PWM in, suppose this is an ideal inductor. If this is an ideal inductor, you look at this one. The blue one is the voltage source modulated as this series of different pulses, like in here, like in here, like in here, right? And then the red one, suppose the red one is the current going to the inductor. Therefore, if this switching frequency is happening, switching frequency means switching between 1 and 0, 1 and 0, and 1 and 0. If this one is happening in a very accurate way, then the current waveform is the integral of the voltage waveform. This is the integral of the voltage wave. So you connect all the on and off, and you can see this is going to be the integral of the voltage waveform. Having that in mind, hopefully everybody can remember the magnetic forces on a current carry wire. If you have, let me just draw that one for you. Suppose you do have some wires like this. Can you remember, if you do have a simple wire, how you calculate force, how you calculate magnetic field, and so? Can you remember the right-hand rule? Very similar to that. I'm going to quickly remind anyone who might not still be aware of that. For example, force is going to be I times B. I stand for current, B stand for magnetic field. If you wanted to draw it, how is that? For example, this is your wire. If this is your wire, force is going to be this one. Just a quick reminder. And then current, I'm going to draw it with a different color for you. This is going to be your current, isn't that? How about B? What's the location or the direction of B? Who can remember that? 100% correct. I'm going to draw that with a different color for you. Then this is going to be your B, right? So that's why we say force on a wire is the product of current times magnetic field. In case you wanted to consider the length of this wire as, suppose L, you can also include the L, which is the length of the wire. This is one of the basic equations in electrical engineering in order to calculate the force applied to a wire. Why I'm bringing this to your attention, in the previous example, I said this is going to be inductor. You know, inductor is a wire, right? Inductor could be a wire, a type of wire. Therefore, if you are looking at the current, which is going to be the integral of this voltage, this is the way we can calculate it. So current is, remember, current is always perpendicular to the magnetic field. Then force is the product of current, magnetic field, and the length of that certain wire. You can remember this from other courses or not? Not, yeah? So it's good that I reminded. Now, some of the application of the PWM, I'm going to bring it to your attention because I'm pretty sure every single one of you are seeing this kind of PWM application all around you during the daily experiences, but you may not know it. So for example, your eye clicker. Eye flicker is something that many of you already probably had it even in childhood. Can you remember it? If you had some bike or something, I myself had it. So eye flicker limits the brightness control. It will look at the brightness control in case you have it. So on average, also you can, kids, do you know how many times you blink during the minute, each minute, as a normal human? Have you ever heard of it? How many times you blink? Maybe 15 to 20 times. As a normal person, we can blink 15 to 20 times per minute. So our eye can detect flicker at a certain frequency, and that frequency is something between 30 to 50 hertz. Each time we blink, in fact, our eye is going to detect flicker between 30 to 50 hertz. So in many TVs, I'm going to even give you an example in TV. So in many TVs, I would say frequency is higher than this. In TVs, frequency is almost around 60 hertz. That's why we don't notice it, because our eye is limited. It is happening inside the TV, but we cannot see it. It is happening faster than what our eye can detect. So for TV is 60 to 100, maximum is 100. And we cannot see the flashing LED in there simply because it is flashing faster than what our eye can detect as a frequency. If you see some array of LED on some bike, like this one, how many of you had something like this in childhood? I myself, I had it in childhood. Some LEDs like this one is spinning like very fast, which is going to be, the dynamic of this one is again faster than our eye. And since it is faster than our eye cannot detect the colors clearly. That's why we see them as a combination of the colors in here. When we spin super fast, the colors are changing. Also, these are like solid color in a stop position, but since it is happening super fast, then we can see it as a mixed color like this. Another application is the digital to analog. We already had digital to analog weeks back. So then we have logic high. This is logic high or 1. And then we have logic low or 0. And we want it to be shown as a continuous, like this one, continuous signal. So we use a simple resistor and capacitor. Remember, we had it before. What we call this one? We are using capacitor and we are using some resistor in order to generate the high and low. We had something similar without resistor inside the hold, sample and hold, right? To sample the voltage and generate that digital equivalent. So we use a filter to remove high frequency and reduce the ripple voltage from the signal, and then at the end just display it as a continuous, this is a continuous signal, which is going to be the digital signal. So we filter out, and that filter is happening only using a resistor and a capacitor. Then what would be your job as an engineer? Your job as an engineer designing a PWM system is being able to calculate what size of resistor and what size of capacitor I can select, and we are going to have problem from this section, and I'll solve them for you to train you how you select the right resistor, how you select the right capacitor to build that filter system. So you can simply filter out any noise. Means you are going to generate a continuous signal by controlling the input signal. And remember, I said initially it was just that potentiometer. Now you are going to use a capacitor as a Y. What was the role of a capacitor in here? Who can tell? For what? Capacitor is holding the voltage. Resistor is dissipating voltage in the form of heat. Therefore, resistor is helping to reduce the voltage. It's going to be dissipated as a heat, and then the remaining one in this one is going to compensate. It's going to hold the voltage. The remaining voltage is going to be passed to the capacitor, and this could continuously happen until we have a continuous signal. Make sense? Yes or no? So since you are already familiar with duty cycle from analog to digital, my life is a little bit more easier in here to talk about duty cycle. Actually, duty cycle, or even they call it duty factor, either will work. Duty cycle or duty factor. This one is the ratio of time a load or circuit is on. For example, here, the ratio of on time over the period. That's what we call it, duty cycle. Means how long the system is on from that whole period. Period means a combination of off and on for a signal. How long, for example, if this is 5 seconds, and probably this is maybe 2 seconds. For me, period means 5 plus 2 means this whole period takes 10 seconds. 10 seconds, I have 10 seconds. How long of this 10 seconds I want to be on? How long? I'm talking about the time, the duration. The duration, that's why we call it duty cycle. How long is on, how long is off? And that's exactly the time that we are assigning to be on and off has direct impact on pulse width modulation. That's why I say it's super important to, as an engineer, be able to design the system in a way that it can perform accurately and safely as an automotive engineer, to define for how long I want it to be off without creating any complicated situation in the road for everybody else to drive in the same place. Make sense? So now, on again means 1 or high. Off means low or 0. In here, duty cycle means look at the on time, not the voltage. On time. And for example, if this is 5 seconds and period is 5 plus 2, 7, this will be the duty cycle. Make sense? Now, if I have a 60% duty cycle, a 60% duty cycle means instead of having on time and period, I'm having the duty cycle, which we had something similar to this in analog to digital. If I have a 60% duty cycle, how do I calculate the on time and off time? Or I would say, how do I calculate the period? So 60% duty cycle is a signal that is on for 60%. I do not put the 60 on the duty cycle. When I say my duty cycle is 60%, means my on time is 60%. Means I have to consider my on time or write in here, this is going to be 60%. If I have this one being 60%, you as an engineer can simply tell me what is my off time? 40%. Now, if you have the off time 40% and on time 60%, you can calculate the duty cycle. Make sense? What would be the right duty cycle? Still with me? So, now, what's the average signal? So far, we learned how to do the duty cycle. Now, let's look at the average signal. Average signal is actually based on high voltage and low voltage. When I say high voltage and low voltage, again, from what we discussed in the previous lecture, that doesn't mean high could be something that I can assign it for any electronic devices which is not created by us. Suppose we are not the design engineer. We are receiving a full, I had this question before. We receive a pre-made electronic device, any pre-made electronic device, which I'm not the designer, the maximum voltage must be provided by the designer. Designer is supposed to consider a lot of other factors in order to define that maximum voltage. The only time I'm allowed to just have this maximum voltage to be something that I can figure it out is the time that I'm the designer. Make sense? So now when I say VH means, suppose I'm starting from 0 to, if this is 5 volts, this is going to be your VH, means the maximum voltage for this device. And what is the minimum voltage? Most of the time, if you look at a battery couldn't be 0 for minimum voltage, because a battery with minimum voltage is interrupting the chemical reaction inside the battery and it will ruin it. Therefore, usually they say if you are going to discharge a battery, minimum discharge most of the time is equal to less than 2.5 volt. In case the maximum is equal, maybe equal to less than 5 volts. I have no option to adjust it. If I come below this, if there is no control circuit, I can come. But if there is a control circuit, automated control circuit attached to the battery, the way it has your, we call it battery management system or BMS. If there is no BMS, you can come down. You can just discharge the battery up to less than 2.5. But if you do so, you are gonna kill the battery, because what you do is impacting the chemical reaction between the cathode, the anode, and the electrolyte, and it will ruin it. Therefore, always look at the data sheet for any electronic devices. Now, PWM alignment in here. I'm going to look at this example. I'm having a voltage range, I just said, between 0 to 5. This is my voltage range, 0 to 5, as an example. Kids, may I have your attention? And then you are going to look at the average voltage. What do I put in here to calculate the average voltage? I have to put the 5 in here and I have to substitute 0 in here. Then simply I can calculate the average voltage in one period, in only one period. Again, one period means only, if I just show it one more time, one period means only from here to here. There are systems that they have many periods. But if you want, for example, if they say, I want it for 10 period, first calculate for one period, take this V average times 10. But this equation applies to only one period, one on and one off. And can I have them differently? One time the period takes maybe 7 seconds, and then the very next time take 10 seconds. Is that something correct? Does that make sense for you as an engineer? It won't. Why is that? Yes. Period supposed to be constant. Even in timer interrupt, I discussed this one. In analog to digital, touched it. We cannot have them to be variable. Otherwise, again, suppose that example of pressing your gas pedal. What will happen if sometimes you press the gas with the same pressure, if you can just keep your feet to be constant pressure and you are not adjusting the pressure, one time it may take 10 seconds, then the next time 7 seconds, the next time 2 seconds, it will cause not a constant increase in the speed. And again, it will generate some interruption for the driving. Now, let's look at, this is the same example. Again, when I say I have a duty cycle, keep it in mind. Tomorrow in the lab, I'm going to give you this example to design a system or to program your DC motor. I'll give you the DC motor is already there in the box, and then I'll get you to program it with different duty cycles. Then I'm expecting you to understand when I say apply different duty cycle, what does that mean? Means just go look at the on time. If 60%, keep it on for 60%, right? And so on. And then probably when I say 60%, again, you have V low, V high. You have to consider that. Now, let's look at this one. Here you can see that we are going to control the speed of DC motor, as I said in the lab. So I'm going to just look at this example to show you what does it mean. So this one is the basic structure of DC motor, right? DC motor or what? Or direct what? Current, right? What is non-direct current? AC. When I say AC means what? Means I'm able to alternate. Can you have any example of AC in your mind? Can I alternate a DC motor? Yes or no? And what will happen if I alternate? Alternate means if this is your X and Y, alternate means just sometimes stay in here, sometimes go down. Sometimes stay in here, sometimes go down, right? Means have both positive and negative. Again, if we are supposed to do so as an automotive engineer for that gas pedal, I'm going to continuously use the same example to make sure it makes more sense to you. What happens if I continuously go up, go down, go up, go down? Again, it's going to be stop, start, stop, start, stop, and dangerous situation. That's why we don't do AC, we do DC. DC means everything, you have to plot it. You have to plot it. It will go up. Everything should be positive. We cannot go negative. Make sense? Why is that? So now, a DC motor or direct current is an electrical motor that converts direct current into mechanical energy. And I know everybody loves mechanical engineering. So we are going to convert electrical to mechanical. How? Through this brush, commutator, coil, and magnet. I don't need to design them in this course, but in case you are, because in automotive engineering, we have, if you're going to work in a company, which is an automotive company, we do have one department only designing motors. Probably very soon we are not going to have that anymore because everybody is working on battery. But still, I can remember during my PhD, we had a whole lab, lots of researchers, lots of other postdoctoral, other faculties focusing only on motor design. And that motor design, it was some focusing on, for example, the coil, some just how to make sure that there is no excess heat, because excess heat and everything is going to happen through the coil or the inductor. So that's why this by itself is a full engineering perspective. Since your microcontroller is not able to generate enough current to make such a DC motor, then we are going to consider a range, and that range is going to be, let's say I'm going to consider the range of 0.1 to 0.5, and then this is going to be amp, means current. You know that amp is the unit for current, right? So then you need to use an interface. Interface means similar to what we did for analog digital converter in order to convert it. Interface means what? Interface means you are going to look at the size of the motor and consider some time for it. And that's why I'm going to get you to become very familiar with a new device tomorrow called opto-isolator. This opto-isolator, DC motor by itself, remember I said it doesn't have the option to change the direction of rotation. It doesn't have that. Now, you guys as an engineer, you want to do so, then use another IC. This opto-isolator, right in here, even they call it optocoupler. Both of them are correct. Isolator or coupler, both of them are correct. This is going to be a semiconductor device which is allowing any electrical signal to be transmitted between two isolated circuits. So in here I'm having a microcontroller, and this is going to be my motor, and I'm putting optocoupler right in between them, which is probably you notice that breadboard on the side, right? On the side of your setup, there is a little breadboard, and in that breadboard, I'm having two IC connected. One of them is the H-bridge, the red one. That H-bridge is for your stepper motor. The little IC, very similar to any other regular IC. It's a little black IC. That's what I call it, optocoupler or opto-isolator. That one is going to help you. You have to connect it to the motor. Tomorrow I'll teach you. You have to connect it to pin 4 and pin 7 and ground. Pin 4 for channel A, pin 7 for channel B, because I have two channels in the setup. Either of this, not both at the same time, plus the ground in order to control the DC motor. So what I have right in here inside this optocoupler, I'm gonna introduce it to you. This one in here is going to be a photodiode. This photodiode is exactly what helps you to go between low and high and generate that pulse. So you're not gonna do it manually. This opto-isolator through this photodiode is gonna just change the signal between 1 and 0 or high and low and create that pulse width modulation. I do have another switching sensor. This is just a switch, and what this one is doing, this one is closing the circuit. Each time that you are generating high, then the switch is gonna close the circuit. It will send it to the motor, right from here to here. And next time it will switch to 0. First, this one will set to 0, switch will open, and then send 0 to the motor. That's how you can create the pulse width modulation through a opto-isolator. So far, makes sense, kids? Everyone got the point? I think it's time to give you a break, and then I'll continue after the break. So if you wanted to just learn a little bit about why we are using the opto-isolator or optocoupler. Definitely, if you know what's the functionality of this little device in there and how it can help the better performance for your setup, it becomes, as I said, more purposeful for you to use it. So let me look at inside this little device, introduce, because you cannot see inside, introduce what's going on, especially for some kids, some curious kids who needs to understand everything behind the scene, and that's lovely. So I'm gonna do, like, open up this device. Suppose this is your optocoupler. This thing include two different circuits inside. These are enclosed inside the same IC. When you look at the optocoupler from outside, you can see just one single regular IC, only 6 pins, not super fancy, not lots of pins in there. But inside that single device, which is this one, you do have two different circuits. I'm going to call them circuit 1 and circuit 2. And remember, we are looking at this to gradually learn how we can use pulse width modulation in order to control the speed of a DC motor. And one more time, remember, in order to control the speed of a DC motor, we need to get access to control the voltage. Still, voltage is not something we can change it. We can have that 5 volt, that 5 constant volt, for example, 5 volt. But what we do is inside this unit or inside the program, we have to come up with some idea, some method in order to pulse it. That same 5 volt, maximum still it is 5 volt. We wanted to pulse it. We wanted to go on and off, on and off, on and off in order to be able to generate a continuous signal out of it. Now, this optocoupler in here, what you can see, this guy has 2 different circuits. I'm going to call it circuit 1 or C1 and circuit 2 and C2. What is circuit 1? Circuit 1, what you see in here, probably you can understand this is, I told you last semester, this is the symbol for a regular LED. But the thing is, this is IR. IR standing for, who knows that? Infrared. This is an IR LED, not regular LED. Means this one's supposed to emit something, right? This one's supposed to emit something. On the other side, what do I have? I do have photosensor. You can call it also photo transistor, because this part, this guy, it should be multiple devices. I'm going to write them down for you. It could be a photodiode. It could be, what else? It's a photosensor. We have so many different photosensors, right? It could be a phototransistor. What else? In here, I say general sensor because it could be different thing. It could be photo TRAIC. This is another different one. It could be photo SCR. These are different photosensors. Photosensors means they can detect some light and they can filter it out accordingly. That's what a photosensor does. Now, if you consider in my first circuit, this 2 pin, which I'm going to show it with a different color, this is a nice story to learn. This is pin 1. I'm going to call it pin 1. And suppose the other one, this is going to be your pin 2, which is already grounded. So this 2 pin that I can show you right in here, pin 1 and pin 2 are the anode and cathode of the LED. Positive and negative. Remember, this one is IR1. And remember, LED has polarity. Everybody can remember that from Mechatronics. Remember, LED has polarity. One leg is shorter than the other one. That's why by default, when I put it inside the circuit, I do not have option to choose which one. It's not like a load. It's not like a resistor. To choose which one I want it to be positive or no. There should be a rule I have to follow in order to get a correct operation. Therefore, this is going to be the anode and cathode. And then if I call this one pin 4 and pin 5 right in here, sorry, pin 3. I have 1 and 2. This is just assignment, or let's say my assumption. 3 and 4. If I label this as 3 and 4, these are going to be the pin of my phototransistor, if it is a transistor, photodiode, or any generally photosensor. And what does that mean? That means this is going to be this P3, which is the positive, is going to be emitter, right? And then in a transistor or any photosensor, I do have also collector. This is going to be, also I'm having the detailed data sheet for the optocoupler being added to Avenue, and tomorrow you can see it during the lab time. If you are interested, you can open it up, you can look at the detail, what pin supposed to do what, and why I have 6 pin, which of them supposed to go to microcontroller, which one supposed to go directly to the DC motor. But still in here, I want you to understand, I'm having emitter and collector in here. Simply means each time this LED inside, and this part is going to be the input, and input in here is going to be what? Input is coming from where? From microcontroller. Motor cannot be input, can be? No. This one's supposed to be connected to your microcontroller, and then the other end is going to your load. In this example, DC motor. Therefore, anything coming from the microcontroller is coming in the format of input signal going to this emitter in here for me, this LED, not emitter. This LED generates some light inside, and then the photosensor, this part, has the ability to detect that light and accordingly just come up with some output on the DC motor. Now tomorrow when I tell you get your optocoupler to be connected to pin 4 in case you are using channel A, and then the ground, now you have that understanding what I say. You don't need me to explain it anymore. You know that either pin 7 or 4 could be the input from the microcontroller. Why 2 option? Because remember on the setup you have channel A and channel B, and there is no difference between channel A and B on the side of the LCD. Remember there are 2 blue parts in there. Day 1, lab 1, I introduced these are your channel. Later we will use them to connect DC motor to them. And then on the well setup, you do have 2 DC motor. Therefore, you can connect either of those 2 DC motors to channel A or channel B. And then if you connect to channel A, grab pin 4 of the microcontroller and then connect it to this one. And then the other end is going to be connected to the ground of microcontroller. And tomorrow also I'll give you the circuit to follow. But still, if you have that understanding, your life is going to become much, much sweeter. So now, anything from here is input, which is coming from microcontroller. Anything on the other side is going to be your output, which is going to be your DC motor. This is the summary of what we are going to do. And then through the input, coming from the microcontroller, suppose you have 5 volts, you are going to get this IR LED to detect that voltage and send it, filter it out to the sensor, and then you are going to have the duty cycle, and then I'll get you to go ahead. You can see it right in here. This is the DC motor driver. I already have that one. Tomorrow also I will show it to you. Inside the driver in here, switching is happening. Means if you are going to look at inside this is a bi-directional control DC motor. This is helping you to switch between clockwise and counterclockwise direction. That's why I added this one. Now, tomorrow, when I'll get you to apply 25% duty cycle or 50 or 60 or whatever, simply now you are going to change the speed through changing the duty cycle. How do you do that? You don't do it manually. You have that great understanding of duty cycle. I teach you today. I taught you already. Right in here, duty cycle means how long you want the on time. Simply in here, now you are expert. You can tell me, When I say have it 25%, means 25 on or high or 1. Make sense? Then you can come up with a different speed. When I say have it 50% duty cycle, means use the MS delay, set it to 50 seconds, means keep it on for 50%, or let's say 50 milliseconds, right? So, and so on. Therefore, you are going to have, in this example, I'm using pin 7. You may want to use pin 4. Tomorrow I'll tell you. Give data direction to A. Suppose this is your port. We don't have port A for the actual microcontroller. This is an example. Suppose you are going to have port A. Then give it data direction to become 7F. Your B is PB0, means port B bit 0 is going to be output. This is your output. This is your input. Output is connected to DC motor. Through this while, I already programmed this template for you. You are going to see it tomorrow. You are going to just change the duty cycle, and through that duty cycle, you are going to change the speed of rotation. This is going to be the task for tomorrow. I'll get you to connect the circuit inside the lab. I'll get you to connect this part of the circuit inside the lab, but the remaining are already set and ready to use. Now let's look at why we do all of this. Well, this is a summary of what we discussed about, yes.
To be backstep, I'm not sure what MTR is.
Which one?
The if statement, we have MTR 1 and MTR 0. Is MTR a port? We're a part of port A?
Yeah, it's a part of port A. I'll explain it tomorrow inside the header file. I'll move to the header file. I'll show you. And of course, this is the register. Remember, I get you to look at the user manual and inside the register, pick the right register, and then sometimes just put 1 in them or 0 into them. That's the same thing. That's why this part is going to be for the lab. Tomorrow during the lab, I'll give you those information about, for example, how to find out the right command in order to generate 1 and 0. And all of those are from user manual for the PWM. Very similar to analog to digital, very similar to interrupt and timer. Remember, I was taking you to that and then looking at those like 8-bit registers and toggle them, and then go find the equivalent inside the header file. It's going to be very similar to that. It's the same thing. Yeah, no worries. Now, why we do all of this? You notice that, as he just said, in the lab, usually if I just go first in here, in the lab, I always give you this information, which is included right in here, just to clarify your first question. So PWM is going to be 8-bit counter for our microcontroller. And that's, again, another user guide. Tomorrow inside the lab, you see it as this one. If you are going to enable the register, very similar to the same method. You have to go ahead, look at the user manual, put 0 and 1 accordingly. If you want to enable it, put 1 in the enable. If you want to disable it, put 0. Generate the hex equivalent. Either command it through the hex, or if it is 1-bit changing, you can command it through max as well. Right? You can mask it or you can hex it. If it is more than 1 bit, only hex. If it is a single bit, you can mask. But nobody asked me, but I'm gonna just bring this to your attention. Can I have mask for multiple bits? Mask is, as I said before, it's just 1 bit, changing 1 bit. But there are situations you can mask, for example, I'm going to say MB1 means mask bit 1, and then say or mask bit 2 and mask bit 3. So you can add and or something in between the mask command, but you can never say mask, for example, underscore in here, for example, PWM E bit 1 and 2. Only 1 bit. But you can have and an OR between those mask command if you are going to treat multiple bits. Otherwise, just hex. Just use the hex equivalent. So going back to where we left, to gradually bring it to a great point, which is helping you to understand tomorrow's lab properly. I was right in here, just a summary of what I said. So when you purchase a DC motor, I'm going to tell you that you have to look at the data sheet of that DC motor. In case you haven't purchased one for your capstone, if that's applicable, please make sure. Look at some information on that one. For example, look at the audio frequency. Look at the, for example, if you have like too low motor, look at the pulse. Look at all of this information are there. Look at the lower limit, higher limit for handling PWM frequency. This is super important. So when you purchase it, make sure in the data sheet, you can see the mechanical time constant. That's super important. Time constant, control system frequency, at least 10 times higher than the control system frequency. Why is that? For speeding up. What if you wanted to speed up to a certain speed? Therefore, you have to have at least 10 times frequency higher than the control system frequency. Control system frequency could be your microcontroller or anything else. So these are important factors. And for the higher limit of the frequency, make sure that you are considering, for example, if your time constant for the motor is 1 millisecond, I'm going to give you one example, which is almost 1 millisecond is how much in hertz. In hertz or frequency, this is almost 1000 hertz. It's almost 1000 hertz, right? How do I calculate that? I said it last week. Frequency is inverter of time. So it's almost 1000 hertz. Then you need to go with over 10,000 hertz. Then go with over 10,000 hertz or 10K hertz. And you may want to go even above, which is like safer for the situation. Even you can go up to 20,000 in order to avoid noise. If you have a higher frequency capability, it will give you less noise. Therefore, pick up a motor that can give you such a frequency, that can handle such a frequency. Now, let's look at this part, which is going to be how we can generate analog signal using the PWM. We want our output to be analog signal. So far, we were looking at analog digital. Analog was the input. Digital was the output. Now, I'm having PWM in order to generate opposite, means generate analog. So, as we discussed, we need to use low-pass filter. Remember what was low-pass filter? Resistor plus capacitor in this slide. Right in here, just as a quick reminder. Oh, I passed it. Right in here. This is my filter. I need to use a filter. In here, I mentioned this filter, which is a combination of resistor and capacitor. We call it low-pass filter. It's going to help me to just remove the high frequency. So this will help me, the high-pass filter, I'm going to remove high frequency. Using that filter, which is just a circuit, simple circuit. Everybody, again, as I said, as an engineer, could just pick up what resistor and what capacitor, I mean the size of the resistor and capacitor, can filter out the frequency for you in a way that you have less noise. Less noise means more accuracy. Make sense? Less noise means more accuracy. Very similar to resolution. High resolution for the analog to digital. Remember I said set your analog to digital to 10-bit resolution. Then you can turn on your RGB as well, because 10-bit has more resolution. It will filter out more voltage. You have more pure voltage, therefore you can turn on an extra component, which is that RGB on the corner of the setup. Here also, if you are having a better low pass filter, you can bring up the resolution. You can bring up, you can have a better frequency. You can avoid less noise. If you have less noise, means you are wasting less voltage. If you have a better voltage, you can power up the device with more voltage. Still you have more. Still you have enough power to power up your system. So if you have the high frequency component and you are going to filter them through PWM signal as a high frequency, like what I have in here, these are my high and these two are my low. High and low. Then we had a continuous signal and we are using, and this is going to be the continuous signal output. And then if we have a continuous signal and we are using method of successive approximation, remember we had it in analog to digital, and that method of inside the compiler, the microcontroller, we don't do it manually. It's doing its job. Method of successive approximation means that sample and hold being connected to the converter, each time turning it to 1 and 0 until we are closer to the input. Remember that? I explained it. So then the filter is acting as the load, like an LED. This filter in here is like LED or DC motor. This is acting as a load. This is analog low pass filter. When I say load, means I'm supposed to get rid of some voltage. And if it is just the circuit is a combination of resistor and capacitor. Resistor and capacitor. Capacitor by default is not load, but resistor is load. But combination of them is acting like a load that I'm going to get rid of some of the excess voltage or extra voltage. That's why I say it's like a load. So we are simulating the analog situation using RC circuit. RC circuit is my filter right in here. And we call it first order low pass filter. First order low pass filter. The actual electrical circuit is going to be this one. This is the way that I'm going to generate analog. So we need to select proper resistor. We need to select proper capacitor. And when I have those two, then my low pass filter has a cutoff frequency. You know the cutoff frequency. Do you? Who knows what is cutoff frequency? Means I can stop right at a certain voltage, not going above that. So then, in fact, I'm going to just calculate this one. I'm going to calculate this one. Cutoff frequency means I'm having a corner frequency. That corner frequency, which is going to be, again, maximum break frequency, act as a filter. So I have just one link right in here if you are interested in that one. And if you forgot it from other courses, just go look at this one. This one is giving you a little bit more detail. That's out of the scope of this course. That's why I included, for anyone who's interested, a link in here. Go watch it in here. So now, next is going to be, suppose I'm having 5 voltage. I'm an engineer. I'm expected to design such a filter to improve the functionality of a circuit. It's simple. We all know what is the voltage relationship with currents and resistor. What was it? IR. Now, all I need is adding the C to the circuit. And I already told you the relationship of frequency with time. So now how do we do this part? Still we have some time, so I can go over this example for you. So cutoff frequency of the first order circuit. In here, this is, again, can be LED, can be DC motor, can be heater, anything that can get rid of some voltage for you right in here. This one, you have to calculate which kind of resistance you want in here. Again, this one also, this resistor, either of them could be heater, resistor, DC motor, either of these two. So, and we are using just the input VO. This is my voltage. This is going to be input. Input is going to the system. I already show you what is gain in a system last week. But again, in order to calculate gain, I need the output and input. So I put them together. So gain, usually we show it with A. Gain in electrical engineering, we show it with A. Is going to be output, which is right in here, over the input. Output over input. So now, if I have output and input in a system, I have to look at the capacitive reactance. Capacitive reactance, again in electrical engineering, I'm going to write it down for you. This is what we call it. C stands for capacitive. X in electrical engineering stands for reactance. In case these are new, take your notes or later come back to the recording. So now, yes, if I have capacitive reactance, if I have the amount of resistor, if I have the amount of C, again, capacitive is the capacitor, is the size of the capacitor. We call it capacitive. This is the capacitor. We have a capacitive here. Then we can simply calculate this one if we do not have it. This one is going to be 1 over frequency of the capacitor, the actual size of the capacitor. These two are different. FC is the frequency of the capacitor. Capacitor is the only device in here that has frequency. So frequency of the capacitor, usually you can find it in the data sheet of that capacitor. If it is learning environment right in here and I'm asking you to calculate, I'll give it to you. Or, for example, in the lab, it is given right in there. So, and then you have frequency of the capacitor, the actual size of the capacitor, then you can go ahead and design your filter. So, and then cutoff frequency, remember I said cutoff frequency is the end of or the break of that high voltage is right in here. So for example, this is for you is the cutoff frequency. Now, let's look at this first example. Still we have time. Let me open the OneNote quickly. It's not something complicated. It's a short example, but it's giving you a lot of understanding about your filter. Just right in here. So I'm going to look at the cutoff frequency of this system. This is a first order low pass filter. Kids, anytime I'm having a resistor being connected in series connection to a capacitor right in here, this is series connection. Why? Because they are having only one common point. So there is a resistor R1 in series with C1. So these two are in series connection. And then I'm having a load. Therefore, this is what we call it, plus a load, any load. In this example, that's R load. If I have this, the combination of these three components, this is a standard circuit. We call it always first order. Do we have more order like second? Yes. That will be more complicated, more advanced, out of the scope of this course, but we do. So this is always a first order. Why we call it a low pass? Because we are going to filter out the voltage and reduce the voltage. So this is a low pass filter. Now I'm going to look at this example. I have been asked to look to calculate the effect of 100 kilo ohm load. Means in this example, right in here, example 1, I have been asked to calculate in the situation that you do have R load to be 100 kilo ohm. Then resistance, what is the resistance for this circuit? In order to do so, remember I have only one equation. Fc means the frequency of the capacitor from here. Fc is equal to 1 over 2 pi R1 C1, and the unit of frequency is always hertz. So far, so good. Now, what do I have in here is, I'm having, if I just substitute the numbers, I'm having 1 over 2 pi. And then from this, I can look at this from the picture, from the circuit, I can find out the C1 and I can find out the R1. Therefore, you can consider it even in here. C1 is, and these are from the circuit. And of course, I have, sorry, this is R1. R1 is this much, and C1 is 0.1 microfarad. Unit for capacitor, for capacitance. What's the unit for capacitance? Yeah, farad. Don't go wrong with that. So now, just substitute this number so I don't guess them. These are coming from the same circuit in the example. Then I have 2 pi times, I'm going to calculate this one to kilo ohm. If I calculate it to kilo ohm, it's much easier to use it. Then it becomes 1.59, right? So then I'm going to say 1.59 kilo ohm for the resistor, and I'm still having 0.1 microfarad for the capacitor. And I simply can calculate the frequency of the capacitor. Remember, as I said, either it will be given, or you have to just use the actual capacitance in farad or whatever you have in here to calculate for the resistor to calculate it. It becomes almost 1 kilohertz. So without the load resistance, the cutoff frequency, I can say now, without the load resistance, the cutoff frequency is going to be 1 kilohertz. This is going to be my cutoff frequency. And cutoff frequency means this corner frequency, from maximum to minimum. The point which is traveling from maximum to minimum. Now, if I continue in the second example in here, now I have another equation to calculate the ripple voltage. What is ripple voltage? Is this one, between two voltage. Voltage traveling between two voltages, what we call it ripple voltage. It's a periodic voltage, just moving from just one point, which is maximum, to minimum. That's what we call it ripple voltage. And then I have an online calculator. I'll go over this one, and if we have time, I look at the online calculator and I show you how, using the online calculator, you can validate this calculation. So now, in the second example, if you consider the ripple voltage is the PWM voltage times 10 to the power of minus log frequency of the PWM over the frequency of the capacitor, then you can look at this one. It's asking now, figure out the ripple voltage, V ripple, in example 1, which is this example, if it is filtering a 10 volt PWM with 10 kilohertz frequency and 50% duty cycle, and then design a filter to make 0.5 volts ripple voltage of a step 1. That's what I said at the beginning. As an engineer, you are going to be asked to design a filter, a low pass filter. Let's do this quickly. So now, I'm having the effect, I'm going to go look at the R load to be 100 kilo ohm. And based on that, just calculate the frequency of the capacitor again. Same equation, 2 pi. And then I have in here, I have 2 resistor, because now I have the impact of R load. Before, it was without the impact of R load. Now, since I have the impact of R load, how do I say it? I have R1 in parallel with R load. Does that make sense? And then still I have the capacitance, which is 0.1, same. Now, what is R load? Now I need to calculate the R load. R1, I have it. It's 1.59 kilo ohm from the circuit, but I do not have this one. Therefore, I have to calculate R load. And I have this one too. Therefore, I'm going to say, this one, I'm going to rearrange it. Then I'm going to say 1.5 or 59, because it is 59 is more accurate, kilo ohm. This one was, the frequency was, remember, 1 point something. If I calculate this one, if I put without, so then it becomes 2 pi R1, 1.59 times this one without load. Without load, I have it already. Without load is almost 1.4.14, 0.014 kilohertz. Now, if I have 1.5 or 59 in parallel with 100K, remember R load supposed to be 100K from the example, then I can say 1.59 times 100. Both of them are kilo ohm. This is kilo ohm. This is also kilo ohm. The unit should be the same to avoid any miscalculation. Then remember, when we have like two resistors in series, it should be the product of them over the summation of them. Can you remember that from basic electronic? If you have R1 in parallel with R2, what would be the R? It should be R1, R2 over R1 plus R2. This is a standard equation which I'm using in case you guys forgot about it. If you want to calculate R total for R1 and R2, it becomes product of them over the summation. You can remember that, kids? So then, if I follow that one, then in here it becomes plus 100. And now if you calculate it, it becomes 1.57 kilo ohm. Therefore, if I draw it, it should be something like this. It should be, this is my gain. Gain is VO over V in and in decibel. So then probably it's gonna be, if this is the 0, my cutoff voltage will be something around here. Cutoff voltage is this frequency. Then I'm having it something like this. So let me use another color. Then this is going to be your FC. Your FC is gonna be this amount. And suppose this is with load, so it's gonna be like this. So now the filter resistance is selected. In here, my filter resistance is this one. It's selected to be much smaller than the load resistance. If you want to see that, then this one should be smaller than load resistance. Load resistance is 100 kilo ohm, but the filter resistance should be 1.57. So I think I'm gonna just stop it right in here. But before that, I finished example 2 for you. Before that, let me quickly show you this calculator. I'm gonna just get out of here. Hopefully I can copy this one. If not, I'll type it. So it's sim.okawa. Sim.okawa. Kids, this calculator, what was the rest? Let me see if I can find it. If not, I have to, I think it should be either of this. Otherwise, I have to type it. This calculator, again, especially if you are going to become a pro. This is gonna help you. So I'm gonna type it because it doesn't help me with just copy paste. So it's gonna be .jp en PWM tube.php. Let me see if I can open it. Okay, kids, I'm gonna finish it up right in here. Stay with me. I already show you how to calculate it manually as an engineer. Just go over the steps, figure out what would be the right capacitance and right resistance for your filter. But in case you want to learn how to use a calculator, this is not going to be available to you using regular calculator, but there is this online conversion in here. You can simply in here define whatever you have. For example, what I have in here, I have it for the frequency to be 10K based on the example. I'm going to get the exact same result. So then I'm going to have the duty cycle to be 50 as it was mentioned. The duty cycle should be 50. And then if I have my voltage to be between 0 and 10, because in here, look at the example is asking for 10 volt. I have to change this one to 10 volt. And then the resistance, it was 1.59 kilo ohm. In ohm is still the same. If you just substitute all of those, and capacitance is 1, then if you calculate, it should give you the same number and the same, like at here, then you have your setting time, then you have your peak-to-peak voltage, you have your cutoff frequency, and you have the final volt to be 5. And here is very similar to, this is your ripple voltage, very similar to this one in here. This is one thing. So pay attention, peak-to-peak voltage should be 1.55. That's the peak-to-peak voltage. You can practice, peak-to-peak voltage means from this point to this point. Means from, if I write in here, means from here to here. This is what we call it, peak-to-peak. This should be 1.5. This is peak-to-peak voltage. You can practice this one. For another example, I'm going to solve that one during the Thursday session. I'll bring this one up again in case you have more questions. I can help you right in there. So I'm going to stop this one in here, and we will continue with more detail on PWM calculation, peak-to-peak voltage calculation, and how to design your filter during the next session. Come see me if you have any question.